Yeah, it's okay. Oh, hello, Bhaiya. We'll be starting the meet in 5-10 minutes. We're just waiting for more people to join.
Okay, awesome. Okay, awesome. Yeah.
Okay, I guess we can start now. There are also some people watching from the YouTube live stream. So, yeah, so welcome everybody. Thank you for being here with us this evening. Today we are pleased to welcome Mr. Bharathwaj Suresh. Mr. Bharathwaj Suresh is an alumnus of BITS Pilani-Hyderabad campus and is currently pursuing his master's in electrical and computer engineering at the University of California, Los Angeles. He is also a Dardwise scholar who has taken up multiple research positions at CIRI, BITS, ISA Bangalore, and Intel Labs. And today he will be sharing with us his expert opinion on the future of computing in a data centric world. So, before handing over the spotlight to you, I would first like to express my gratitude to you on behalf of all the three student branches for taking out the time to give this talk. So, with that, I ask all of you to give your full attention to Mr. Suresh. Over to you, Bhaiya.
Yeah, thanks, Satvik. First of all, is my audio clear? I just want to get there.
Oh, yes, Bhaiya, it's clear.
Okay. Yeah, so I mean, thanks a lot for that introduction. And not a lot of people call me Mr. I mean, I'm probably just a couple of years older than you guys, so I'm basically still a student. So you can just treat me like your friend. And also, I'm not an
Yeah, sure.
expert in that field, definitely. So I mean, the aim of my talk is just to motivate people. So there are a lot more people who technically can be called experts. So again, yeah,
Yeah, I'll keep. Yeah.
that's yeah. So let me share my screen. So can you see my screen?
Oh, yes, Bhaiya, we can see it.
Okay, great. Yeah. So okay. So what I want to cover today is more, it's not going to be like a lecture. So I'm not going to talk too much in detail about anything. So I'm just going to talk about the area of computing, basically what all you need to know in computing, and where computing is headed. So because I think we are in a position today where computing is going to change drastically in the next few years. So that's where computing is right now. So it's very important to understand like why we need to change, and how we are changing. So it's going to be a very like abstract and top level talk. So I'm more interested in the Q&A, so I'll probably get through my slides quickly, and if you guys have questions we can discuss a lot more based on that. So yeah, I mean, first of all, a little bit about me. I mean, Satvik already mentioned a few things, but yeah. So basically, I'm now an MS student in electrical and computer engineering at UCLA. I started just this September. Before this, I worked for a year at Xilinx. I was working in the data center group, and we were working on designing an IP to, accelerate data transfer in one of Xilinx's products. And before being at Xilinx, I did an internship with Intel Labs. So, I mean, this is a really a good one and very relevant to the talk. So, I worked on some really cutting edge stuff. So, I'll probably talk about this a little later in more detail. And I did my undergraduate thesis in IISc Bangalore, and I worked on neuromorphic computing. So, initially, a lot of what I did was based on neuromorphic computing. So that field is very special to me. And again, I'll be talking about that a little bit more later. So I'll just skip that. And yeah, uh, I mean, to start off with, I started off like a lot of people here. So I did my undergrad in its Pilani-Hyderabad campus in electronics and communication engineering. So yeah, I mean, this is who I am. I mean, there might be a lot of questions about a lot of things here, so I'll be happy to answer that in the Q&A if you're curious to know what I did where and things like that. So yeah, so I mean, now I'll get to the actual part of the talk. So I mean, I just want to start with talking about how computers work, and I mean, nobody is able to actually answer this question how computers work, because if you know exactly how a computer works, I think a lot of people will be ready to pay you a lot of money, because that's one of the most complicated topics today in the world. But I mean, what I'll be presenting is a very abstract view. I'll be talking about the different layers. So this diagram is something Like if you take any computer architecture class in any part of the world, this will be the first slide you see, and they talk about these abstraction layers and designing a computer. So I mean, it's a very cliched thing, but it's very important to understand, because each layer has a very specific purpose. And yeah, I mean, so I mean, the current way computer architecture thought is, you expand this view. So initially, computer architecture was just hardware software interface and microarchitecture, which means basically how the hardware is within your computers and how you write like instructions to execute that hardware. But now computer architecture is extending to a lot higher. I mean, this diagram says it goes up to algorithms and devices. I'd say, problems, electrons, everything comes under designing a computer now, because it's becoming more and more challenging, as time is going on. So, I mean, I'll just talk about each of these layers a little bit. It's very obvious, but still, just want to cover it. So, I mean, first thing is problems. So, I mean, a lot of engineers, we sometimes forget the problem, because we think engineering is all about the lower part, like writing code, like designing hardware, whatever. But I mean, the problem is actually the most important thing. So the reason we all do so many things is because we identified some problem and we want to solve it. So I mean, I just want to emphasize here that don't forget that coming up with the problem and identifying the problem is actually one big step in engineering or designing computers or whatever you do. So I mean, as engineers, we have to try and uh, understand what problems are. The next is algorithms and programs. So this is sort of very obvious, because uh, a lot of people get into software engineering, and algorithms and programs are the way you get jobs. And algorithms and programs are actually very important. I mean, even though I come from a very hardware background, I mean, I'm not going to say hardware is more important than software or something like that. Software is actually very important. The only thing is, so a lot of times in software engineering, people want to write efficient code. But when they say efficient code, they forget the fact that it's actually running on hardware. So, I mean, whatever you learn in programming, at least at the undergrad level, usually just talks about, like getting a faster result or things like that. But it's sometimes quite important to understand the underlying hardware and write code which is suitable for the hardware. So, I mean, the reason this is important is uh, it's quite easy to do at this level than it is below in the stack. So, I mean, what happens a lot of times is people write excellent algorithms which are very useful, but they struggle to run on normal hardware. So then you can't change the algorithm now because it's already widespread, and a lot of people are using it. Then it becomes a challenge because you now need to start changing the hardware to suit the algorithm, which I feel is a lot harder than, say, writing an algorithm for hardware. So, I mean, this is again an interesting point just to keep in mind. So even if you're a software guy, just try to understand the hardware. You know, I mean, a lot of computer science courses everywhere have a computer architecture course. There's a reason for that. They want you to know what the hardware is and write good code. So, I mean, coding, especially in the coming years, is going to be more about hardware. The next is, of course, the interface between hardware and software. Uh, I have actually not worked in this area as such, but I have a lot of respect for people who do this, because truly they are the only ones who need to know both hardware and software. So I mean, we can say that we want to work in the entire stack, but a lot of times software engineers just do software, and like design and micro arc engineers just work on the hardware. So, but I mean, if you're working on the hardware software interface, that is, if you're designing some system software, like embedded C code or something like that, or you're designing the instruction set architecture, which is basically instructions to run programs on your hardware. So I mean, if you're doing something like this, there is no choice but to know how the software works and how the hardware works. So I mean, it's an extremely challenging area, but extremely rewarding, because how someone does in the hardware software interface basically determines how easy it is going to be for a software engineer or a hardware engineer. Because if you don't have a good interface, either your hardware should be more complicated or your software needs to be more, low level, which means it's difficult to write code. So, I mean, this area is underrated, but it's definitely something which people need to focus more on. And I mean, I would say one of the most challenging areas in this whole stack. Then is microarchitecture and logic, which is actually, I mean, primarily what I work on. So this is basically, your digital logic and architecture behind your computers. So yeah, it's basically what all your programs run on. So, I mean, if any of you have experience writing a very log code, etc., that's all to do with this. So, and basically, yeah, you write the code here and you can tape out the chip. So that all comes under this level. And yeah, I mean, this is very fundamental and you definitely need it. So, I mean, there is no shying away from this. It's and I mean, I'd say this is sort of the equivalent of programming and algorithms in the hardware level. So just like how like software engineers need to write efficient code, people who work at the microarchitecture and logic level also need to write efficient RTL code. So I mean, that's also a very important skill, and something that people need to work on definitely. And yeah, the last level is devices and electrons. Yeah, again sometimes when you're working in electronics, you sometimes forget the fact that fundamentally everything is happening because of a transistor and electrons in the transistor. We have computing today only because somebody came up with a transistor. This is a photo from Bell Labs. I mean, this is a story almost everyone in this industry knows. So, I mean, the reason we are actually moving to a different form of computing today has a lot to do with devices. So, I mean, the same devices that got us to where we are actually, letting us down a little now. So that's why, I mean, I feel this is a big area, and this is so. I mean, the way let me just go back to the stack. So the way things work in the stack usually is changes at the lower level are always much tougher than changes at the top level. So like coming up with a new device to perform computing is a once in a lifetime thing, but coming up with new algorithm happens almost every day. So and the point I'm trying to make is this area is definitely worth working on. You'll probably get very slow progress, but even a small progress made here, it has like a ripple effect, and the improvements you get are immense. So, I mean, let's say somebody comes up with a new device to replace transistors, which is much better in like whatever way. You are probably going to get like a 6 or 7 orders of magnitudes improvement in your like algorithm implementation. But I mean, if you just implement a new algorithm, your speed up is going to probably be 2x or at max 10x, nothing more than that. So I mean, always remember that lower in the stack is harder, but it gives more breakthroughs. So I mean, that's the idea of computing. And okay, so I mean, this the computer design industry is actually one of the most efficient and well planned industry. They people are very clear about what they want to work on here, and like the interactions between each levels is like really well done. So I mean, if you just work at a end to end company like I don't know, something like Google or something, where they work on everything from problems to devices. I mean, the way the industry works is actually, that itself is quite beautiful. So, I mean, if everything is so great, then I mean, why am I even giving this talk? Like, so, I mean, the problem is that things are changing a little. Our applications are becoming different, and there are a few issues which are coming up. So, we need to slightly rethink the way we are, dealing with computers and computing in general. So, I mean, the first big problem, and this deals with sort of the device level. That is, scaling is slowing down. So scaling basically means reducing your transistor size. I mean, a long time back, sometime in 1960s, uh, so Gordon Moore, he was at Intel. So he came up with this empirical law. I mean, it's not even a law, so it was more like a prediction. So what he said was, the number of transistors in any chip is going to be doubling in every 2 years. And he just came up with this based on some like empirical studies and looking at how the trend is. And as it turned out, for a lot of years, almost 50 years or so, this trend kept continuing for whatever reason. Maybe people just wanted to stick to the trend, and they kept following it. So I mean, that made life a lot easier. So I mean, for engineers, maybe something around 1980s to 2000s. I mean, I don't want to demean them, but it's just that you know they could keep scaling their transistors and putting more transistors in the chip. So automatically each time you get more compute, like faster execution, lower power. So things were going very organically. So you know the I mean, the computer hardware industry was, I'd say, it was a lot easier to survive in, because you had scaling was never letting you down. But yeah, now we are around the 5 nanometer range, and here there's a problem. So 5 nanometer means you have about 20 to 25 atoms in 5 nanometers, and that's really small. I mean, how lower can you go? Like, there are some people who are saying, they can do computing with just one atom or something like that. And, I mean, even if you say that, you have what, around 4 years, 5 years, or I mean, rather 4 cycles. So that means about 10 years. That's all you have left. So, I mean, what do you do after that? You can't scale. So it's time to think of something else beyond scaling. And I mean, even at levels like 5 nanometers, there are some issues we are facing, even if we want to scale further. One very important thing is dark silicon. So I mean, what's happening now is, you're able to scale the transistors and put in more transistors in the chip, but the problem is you're not able to scale the power at the same level. So that's because, as the chips becomes more dense, uh, the heat it produces starts increasing. So I mean, if any of you have like heard about the levels of heat that is produced in a microprocessor, it's immense. Like, all microprocessors have some sort of cooling mechanism, otherwise it'll just melt. So you definitely need that. And now what's happening is, like, we've reached a point where we can't cool them anymore. So, I mean, the way we work is, like, let's say you have a big chip with, I don't know, like 10 cores. But because you can't cool everything, you can actually run only 5 cores at a time. So, I mean, the remaining 5 cores are sort of off, and that's called dark silicon. So, I mean, even though you have a chip with, these companies like Intel, Apple, they come up with all these specs. They say, we have this many cores, we have this many transistors. But the truth is, a lot of times, uh, they don't use all the hardware. They can't, because power density is a big problem now. So I mean, scaling is a big thing, and so because of scaling, we definitely need to change something. Another issue is this memory bottleneck. So initially, I mean, when they came up with the idea of computing, so it was very clear and it was very simple. So there's an input, there's an output, and the CPU does processing. It takes values from memory, it does some processing, sends it back to memory. So it's a very simple, very obvious idea, and it's been working very well till now. But the only problem is, slowly over time, what people realized is, this memory to like logic transfer, that is, taking data from memory, putting it into logic, and then sending it back to memory. It's very expensive. So, I mean, just to give you some practical idea, I'd say like memory transfer is at least 50 times more time consuming than performing compute in CPU. So that's becoming a big problem, because a lot of applications today are memory intensive. So, I mean, I'm jumping ahead a little, but yeah. So, I mean, if anybody has experience with machine learning, you know that you need to get in a lot of data at the same time, and the compute is pretty simple in machine learning. So it's basically just addition or multiplication, nothing more than that. So the big thing in an application like machine learning is getting that much data into the CPU. So I mean, that's why using CPUs for machine learning is very inefficient now. So because each time you get data into memory, send it back, you're actually spending more time in that transfer rather than actually doing the compute. So we actually need to rethink this whole design. So this is called the von Neumann model, and a lot of new approaches are being taken to move this memory somewhere else or something like that. So I mean, we'll talk about that a little bit more later. So anyway, this is also a big problem. And yeah, the third problem is sort of obvious, and it's what's mentioned in my title. So we're in a data-centric world, so there's data everywhere. I mean, I was just reading some of these stats yesterday, and it was just staggering. I mean, there are more bytes than the number of stars in the universe, like 40 times more. So, I mean, these are crazy numbers, and I didn't even know what a zettabyte was. So apparently, it's 10 per 21 bytes, and we have this much data flowing around. So, I mean, if you just take out your phone, you'll realize that you have so much junk which you didn't even realize you had. So, I mean, there is just so much. So, internet is becoming ubiquitous today. So, almost everybody has access to internet, and because of that, data is flying around everywhere. So uh, I mean, you need to uh, do something with the data. So either use it to get something meaningful or store it efficiently, something like that. And the way current computers are designed, they won't last with this much of an explosion in data. So I mean, this is not a computing problem, but so here's the thing. I mean, people could say today that, right, I mean, I like my computers the way they are. I don't want to do anything else. But the problem with that is data keeps coming in, so you have to change. Like, this is more forcing the change. Like, it's not giving you an option. The other two are options. So, but with increase in data, you need to design better computers. There's no other choice. That's the only way to survive. So I mean, and there are also more environmental reasons, like data centers cause a lot of pollution. They consume a lot of power. So if you can manage data better, it's going to be better for the world in general. So I mean, these are the big three problems, at least according to me. There are many more problems. I mean, I'm not talking about things like security and all, which is actually quite big now. So I mean, just to give you an idea, like I mean, we have a lot of very interesting machine learning applications today, but a lot of industries cannot use them because machine learning is not yet at the level of security that you want. So, I mean, a lot of work is going into things like encryption and having encrypted hardware so that, people can't steal your information. So that's a completely different side to it. But I mean, I want to focus more on efficiency, power area. So, I mean, so security is again a problem, but I'd say security is a bit of a luxury. These are more, needs anyway. So, yeah, I mean, these are the problems. So, what could be the solution? So, I mean, over the years, the solution has always been to improve at each layer. So, I mean, at every level of the stack, you have experts. So, I mean, every company would have like a principal researcher, a scientist, or someone who's, I mean, let's say Google has some scientist who's working on their search algorithm, and he comes up with an improved algorithm. And okay, so all's good. So the algorithm works beautifully, and they're able to get some 10x improvement in speed, power. Everybody's happy. That's how the world is working until now. But the problem is, I we are now reaching a point where just changing things at one level of the stack isn't really helping. We now need to start thinking about cross-layer improvements. So what I mean by that is uh, the layers should start interacting with each other. So I mean, let's say you're designing some new machine learning algorithm. You also need to parallelly think about what would be the best hardware to run that algorithm. So, I mean, a very simple application of that is, which a lot of people are doing now already, is like coming up with like algorithms which can be easily parallelized. so that they can be run on GPUs. So it'll be more efficient. They'll run quickly, something like that. So, I mean, that's the sort of thinking that needs to go on from now. So, I mean, what I want to say through this slide basically is you cannot be an expert in just one layer of the stack and expect to survive in this industry now. You actually need to explore multiple layers and find solutions which are a combination of both. Those solutions are the ones which are really the powerful ones. All right. So, yeah. So, I mean, these are just some solutions, and these are things I've sort of worked on. So, there are, again, this area is so vast. I mean, there are so many solutions. I'll just talk about the things I know and, what I mean, things that are very close to my heart. So one idea is just to say, right, I mean, who said you need to compute like this? I'll just change the way I perform computing itself. So this is like a top-down, like changing the complete stack. And one of that, which I mentioned earlier, is neuromorphic computing. So, I mean, if anybody hasn't heard about neuromorphic computing, when you first read about it, it feels like science fiction. So, I mean, what they claim is, we want to make a computer which mimics the brain. So, I mean, it's a very, very bold claim. But the idea is our brain is essentially a computer and it's working so efficiently. I mean, even today, there's no computer which can match the brain in terms of, especially in terms of the like power consumption. Like, I mean, we are surviving on very limited energy, but we perform so much compute every day. So the idea is to say, right, I mean, we'll just explore the brain and see what it's doing and just copy it. That's all you need to do. And yeah, I mean, this requires changes at all levels, right, from devices to algorithms. That's what makes this a very challenging area. But at the same time, uh, if it works, it's going to be big. So I mean, it's definitely something worth reading about and exploring. So I mean, the basic idea, I don't want to go into the details. So you can look up some lectures on YouTube or something like that. But yeah, I mean, the basic idea is, I mean, in our nervous system, you have neurons and synapse. So I mean, we build structures similar to that with circuits, and they're used to perform, memory and compute together. So and all the information, instead of storing them in terms of like your binary digits, how you have in computers, they're stored as spikes. So I mean, if you just want an example, let's say you decided that 10 spikes are what is going to be used to store your data. So in the 10 time period, if you have 5 out of the 10 spikes which are high, that means you'd have a probability of 0.5 or something like that. So again, you can decide how you want to store the information. You can decide how you want to compute. This is a completely new paradigm. So, I mean, people are doing all sorts of random things, and everything is accepted. So, but yeah, I mean, the overarching idea is mimic the brain, like be like the brain. So, and yeah, so there are something called learning rules again. So you have data, you have compute, but how do you actually do something with that? So again, we use the spikes and we say, okay, so if one spikes comes, well, there's a pre-spike and post-spike. If they come together, then what do you need to do? So things like that. Again, I'm not going over the details, but this is the idea. And yeah, so I mean, neuromorphic computing is actually not very prevalent in the industry because, like I said, it's a very big change. So, if you want to make a change like this, you first need to convince everybody at the stack that this is worth doing. Because if I say I have a neuromorphic chip today, but somebody in the software industry says I don't care about your neuromorphic chip, I'll write the code the way I do, it's not going to work out. So I mean, making a change like this needs people at every level to contribute. So it's going to take time. But yeah, I mean, Intel has this chip called Loihi. There's actually a Loihi 2 which was launched just a couple of weeks ago. So this is one of the most I mean, famous neuromorphic chips I know. There are a few others, but yeah, I mean, again, it's a very early stage of neuromorphic computing. So essentially, they just have a neuromorphic core to do some acceleration within the chip. Again, yeah, I mean, if you're interested, definitely read about this. They have a lot of resources. And yeah, I mean, that's about neuromorphic computing. So the other idea, and this is specifically at the device level, and I already alluded to this a little before. Uh, Transistors have this problem of scaling and multiple other problems. So you could just say, right, I mean, I'm going to replace transistor with something else. And so, I mean, one of the big areas which at least I worked on is non-volatile memory. So, yeah. Okay, so I'll probably run a little because I'm running late. So, yeah, non-volatile memory basically means that, you have some bits stored in memory, and yeah, so usually in your SRAM or something, if you store a bit and turn off the computer, the bit goes away. It's not stored. But in non-volatile memory, even if your power is off, the value remains. So this is quite important because there's this new area called in-memory computing, which is big. So, like as I said before, the problem with current computers is you need to transfer data from memory to compute and back. So people decided, right, I'm gonna just do compute and memory together. And to do that, you need a lot of non-volatile memory. So you cannot have SRAM here and do in-memory computing. People are trying to do that, but it's not as efficient as having, a non-volatile memory. So that's why it's important to find devices which are suitable for getting NVMs. And a memristor is one big device. It's dubbed as the fourth fundamental circuit component. There's a lot of physics involved here, so I mean, I'm just going to skip through all that. But it can be used for both analog and digital applications. So I mean, this is like the IV curve of a memristor. And if you see here, it has multiple states in the analog domain, and it can be used there. Or you could just directly say I'm switching from here to here as a digital application. So I mean, memristors are quite interesting. There are some issues with the fabrication and reliability part of it, but if people can figure that out, then they are good competitors to transistors, definitely. And yeah, I mean, NVM is actually there. So you can actually go to Amazon today and buy an NVM memory, if you want to put it in your a laptop or something like that. So that's the level we are in. So we are almost, using NVM. But again, I mean, I'm not sure about this, but I heard NVMs are a little slower and they're not as reliable as your normal SSD or HDD. So I mean, people are working on it, but yeah. So if you're interested, you can check out Intel. They call it persistent memory because I think non-volatile memory sounds too techy, and even if when you're selling it, you always go for these marketing terms which sound better. So yeah, I mean, a lot of companies are making these chips. So NVM is definitely one for the future. The other is application-specific computing. Uh, so the idea here is basically designing hardware accelerators. So this is one of the big areas in companies now. Everybody wants to design hardware accelerators. So, I mean, the idea is usually you have a CPU memory input output, but now you're adding another component called the hardware accelerator. And if there's a task that the CPU feels is too laborious for it to do, it just sends it to an hardware accelerator, which is designed specifically to accelerate that task. So, I mean, people have become very clear now. So it's difficult to make a general purpose computer more efficient because that's the ideal case. You make the best computer possible, but it's a lot easier to say, okay, I have an application, so it's convolutional neural networks. So I will just make a hardware which is good for convolutional neural networks. That's a much more simpler problem to deal with, and that's why people are coming up with this custom chips or hardware accelerators. I mean, this is an example of a systolic array. I'll just quickly tell you how it works. So you have a few, okay, so the idea of systolic array, systolic is usually refers to the heartbeat. So they want data to flow through the array the way blood flows in our like body. So something like that. That's how the name came. So anyway, the idea is once you get in some data, you want to make full use of it before you send it back. So I mean, in case you want to perform some matrix multiplication like this in a normal computer, it'll read A11, it'll read B11, it'll perform the multiplication, it'll send that sum back to the CPU, then it'll take that sum back and add it to the next term and so on, which is very inefficient because, like I said, a memory should be conserved. So I mean, the if you need to just take away one thing from my talk, it would be that do less memory accesses. Like if you do that, your computer becomes more efficient, and that's what they're trying to do here. So I mean, just if you see this example, they're getting A14 here and B14 here. These are two inputs. P here refers to something called a processing engine, which in this example is just, like a Mac operation. So multiply and then accumulate the value. So you do A14 into B41, which is actually this term. And in the next iteration, you do A13 into B31, which is this term. And so here, the beauty is you don't send this A14 back. You actually send it to the next P so that you can do A14 into B42, which is being used in this other term. So that's the idea. So once you read A14 from memory, you make full use of it before you send it back. So you'll never have to read A14 again. This is actually the heart of, all hardware accelerations. Like if you get something from memory, don't waste it. So that's the simple idea. And yeah, I mean, this is big in industry. So I mean, you'd have heard of a lot of these things. So Google TPU is actually based completely on systolic arrays. So I mean, these are all external components. They're not important, but this matrix multiply unit is the big one, which is saving a lot for them. So yeah, I mean, just another trend with hardware acceleration now is a lot of companies want to build their own accelerators because that's how valuable accelerators are becoming. So, I mean, Google could have very easily gone to somebody like Intel or Nvidia and said, okay, I want to make my search or my machine learning tasks faster. So, build a hardware for me. But because of the demand, a company like Intel or Nvidia will charge them a hefty price and it'll not be up to their standards probably. So, I mean, Google has decided, they want to design their own hardware. That's why they came up with TPU. And in the new Pixel phones which are coming up, they actually have a TPU like tensor processor, which is quite exciting actually. I mean, so this is not just, for some random applications in the server. It's actually coming to our phones as well. So TPUs are really exciting. And yeah. I mean, so there's something called a wafer scale engine by Cerebras. There's also something pretty cool. So usually, yeah, when you actually make a wafer, so you have multiple chips. So usually each of these squares is one chip, which is the size of your typical processor these days. But what these guys in Cerebras said is, okay, I don't want such a small processor. Just give me, huge compute and huge, like large number of cores. Like let the whole wafer be a processor. So this is a very, very unique idea. The only issue here is if one of the dies here, I mean, so one of the small chips, whatever I showed you, if one of them doesn't work, this whole wafer scale engine doesn't work. So, I mean, usually in a processor, if one of them doesn't work, you just throw that one away and use the others. So, I mean, actually making this is quite challenging, but I mean, you can read about this. So they have a lot of interesting ways how they tackle this problem. And of course, there's the OG hardware accelerators. So you have GPUs, FPGAs. These are old technology now, so I'm not talking about them, but they are, technically how hardware acceleration started. So again, it's good to know about these as well because they're quite fundamental to the idea of hardware acceleration. And last one is I'm just going to go very quickly. So this is something I worked on at Xilinx. So mm, so now this is more at the system level. So you have a lot of components and everybody's sending data to the CPU or hardware accelerator or something. You need to actually manage that properly. So I mean, the word traffic here can be taken literally. So I mean, if you have traffic in a road, you have signals to actually manage the cars moving so that things happen efficiently. It doesn't happen sometimes in India, but that's the way it's supposed to be. But yeah, so the idea is you need to design a hardware which actually manages this data flow. So designing this hardware efficiently is also a big thing. And there's this AXI protocol which is very famous in industries. Almost every hardware uses this protocol. And designing a hardware to make this AXI protocol efficient is what I worked on at Xilinx. And it's definitely something worth pursuing because usually when you say computers, people forget about this, but routing in computers is actually a very important thing. So yeah, I mean, I think I went beyond my time, but yeah. So the basic idea, this should be the summary of the talk, and I think I'll have a lot of questions on this. So if anybody wants to get started on this field, if you think something I said is exciting or something, so I mean, this is your answer of what you need to do. I mean, first thing is your courses are important. Just try to go through them. I mean, not necessarily for the grades, but You need some fundamentals before you can jump into these things. They're not that obvious. So I mean, if you want to explore new computing architectures, you need to have some idea of how the existing thing works. So those you get through courses. I mean, our lectures, undergrad lectures, are pretty good to get started with. So definitely, don't ignore them. And you have a lot of content on YouTube as well. So I mean, I'm a big fan of Professor Onur Mutlu. So he has all his lectures. I mean, the lectures he gives at ETH Zurich in every quarter, it's always available on YouTube. I mean, that's an invaluable resource. I mean, not everybody can get to ETH Zurich, but I mean, if you just go through his lectures, it's as good as being there. So, and he covers a lot of a state of the art content. So you won't get stuff like that anywhere. So it's definitely worth checking out. And yeah, I mean, the good thing about being at a place like BITS or an IIT or whatever, I mean, when people ask me what's the best thing about BITS, I always say that it's the people I met. I mean, the courses are good, there's a good brand value, good companies come and all that. That's all secondary. But you meet a lot of excellent people who are just as motivated as you. So keep talking to people around you, keep talking to them about what they're interested in. You don't know who's going to do what. I mean, don't judge someone before you start talking to them. Just talk to anyone, get new ideas, discover more new things. This is the best time you will get to actually discover new ideas. So I mean, just talk to people, talk to seniors, talk to people in the industry. I mean, I don't think anybody is gonna refuse, especially somebody who's confident about their field, won't say no to sharing their ideas. So definitely find people to talk. And yeah, in the spirit of me saying talk to people, this is my LinkedIn profile. So just hit me up if you want to discuss anything. Of course, we have a Q&A too, but yeah, this is for later. And yeah, I mean, the best way to learn and build up a profile for yourself is to do projects and internships. These are more valuable than courses. Courses start you off, but this is what take you to the next level. uh, I mean, the only thing I'd like to say here is it is okay to start small. I mean, this is obvious, but a lot of people don't understand this. uh, when you're not going to directly get an internship at MIT or something when you get started. You need to start small. So I mean, it's fine if you're just doing a project in undergrad at your university or something like that, or even a course project for that matter. Start with that, use that to get other things and keep growing. That's the only way you can reach a certain level. you it's very rare that people directly get big opportunities. So I mean, I just like to end by saying, stay patient. uh, I mean, if this is the area you want to work on, I'd say, this area is really big now. I mean, don't worry about money or anything. If you're good at this area, like there are 1,000 people who want to hire you and pay you a lot of money. So this is this is one of the biggest area in computing right now, which is making computing more efficient. So just stay patient, try to understand the basics, and keep talking to people again. So the more exposure you have, the better it is. So I mean, that's pretty much what I had prepared. Uh, I mean, so we can go to the Q&A now. Uh, so yeah,
First of all, Vaya, thank you for giving this talk. As somebody who is into this field, I found the talk very inspiring. I'm sure the others also found it inspiring. I think you gave a very good brief introduction to all the different domains that are included in the stack that you mentioned. And I just have one question. So,
yeah.
do you think it would be reasonable to expect that companies such as Facebook and Google, which were
Mhm.
once very software centric, will move more towards the hardware side of things, like how Google designed its own machine learning accelerator?
Right. So that's already happening actually. And I mean, like I said, so those kind of companies, they have two choices. Either they could get a hardware company to do something for them, or just say, right, we are going to design our own hardware. The problem, so I mean, a company like Google has a lot of resources. Even a company like Facebook has a lot of resources. So I mean, the way they would think about it is to say, right, I mean, why should we take the other companies uh, technology and use it? Because that way they'd be dependent on the others. So this is more a business thing than a technology thing. Because at the end, these are companies doing business. They don't really care if they're making the technology better. They want their company to be the best. So definitely companies are going to get more hardware centric, just purely in terms of jobs also. If you see, Google has started hiring for a lot of hardware positions. Facebook has, there's something called Facebook Reality Labs where they do a lot of hardware work. So yeah, especially with hardware accelerators, every big, the FANG companies, so all of them want to, design their own hardware for their applications. Plus another thing is they don't want to reveal too much of their applications as well. So, Facebook might have some copyrighted algorithm to do search, and they'd want to design hardware specifically for that algorithm. So if they want to work with a different company, then they'd have to actually reveal that algorithm, which they may not be comfortable with. So I mean, yeah, just to answer your question, yes, definitely companies are going to be more hardware centric. All companies.
Yeah, thank you for that insight, Bhaiya. And also, those who have any other questions, you can either unmute yourselves or you can type your queries in the chat box. And those who are watching from YouTube, you guys can fill the form. There's one question from the form. So
Okay.
the question is in-memory computing used in current technologies? If not, what are the problems that something like this would take to integrate with the current technology?
Okay. So in-memory computing is actually more a terminology in the sense that, there are many ways to do in-memory computing. So when I say in-memory computing, at least, what I mean is just combining memory and compute and like so yeah, I mean, you take usually memory and computer separate, but now you say, right, I mean, I do compute within the memory itself. So that's the idea of in-memory computing. There is also something called near memory computing, which is actually more prevalent. So near memory computing means that it's a simpler idea. So you still have memory and compute which are separate, but you have a very fast memory which is very close to the compute. So like I mean, if you have an understanding of computer architecture, so you know that there are registers, and registers are very close to memory and they're super fast. So you could have a lot of registers close to memory and then say, right, I mean, whatever I need, I'll keep it in the register and then use it directly. So that's still pretty fast. It's not in memory computing, but it's called near memory computing. Uh, so I mean, your question was whether it's used in the industry. I would say something like systolic array is also in-memory computing because I mean, as I told you, so like the data comes in, you do some compute, you need to store that partial value somewhere, so that is stored within the memory. So I mean, that's the idea of like in-memory computing, and that's the level at which it's being used now. Almost all hardware accelerators have in-memory computing embedded. So I mean, like I said, the theme of today's talk, or today's, I mean, the computing in general is don't you do memory access unless you need. So that's why everybody wants to store things close to memory and use it. Pure in-memory computing will come in only when the devices change. So I was talking about non-volatile memory. So if you have a very like well-performing non-volatile memory, then you can actually do compute in your non-volatile memory. So I mean, I have worked on some projects where we've used memristors to perform I mean, as both memory and compute. So the advantage with memristors is it's a non-volatile memory. So if you just put some value there, it'll stay there. But at the same time, I can uh, uh, perform some compute and change that value to something else. So that is what pure non-volatile, I mean, pure in-memory computing is. Again, I'd say it's still in the research phase because these devices are not reliable. But yeah, I mean, near memory computing is more, practical today.
Okay, but thank you for that answer. I have one more question from the forms. So the question is, how can I get started with learning about neuromorphic computing? Topics like these are usually not included in most undergraduate courses.
Yeah. Neuromorphic computing is a little challenging in the sense that there are very few resources for it. There are very few, at least, official. I mean, you don't have something like a book or something for neuromorphic computing, which is a problem. So, I mean, I would say, I mean, first, you can look at a lot of these keynote speeches, especially in these big conferences. So, I mean, like let's say, for example, I told you like a couple of weeks ago there was this Intel Loihi 2 launch. So I mean, you can just check out their group, and they'll have a lot of resources and talks about what their chip is and what it does. That's more the top level stuff. So I mean, that will give you an idea of what neuromorphic computing is and whether you actually like it or not. After that, what you need to do is little bit of grunt work. So the only way to get into these fields is through research papers and things like that. So I mean, as a beginner in research, I would always suggest people, if you can find a good thesis, look at that. A thesis is definitely, better than a research paper because it has a lot more information. So maybe, find things like a thesis or a research paper in neuromorphic computing and read about it. But yeah, I mean, so my suggestion for things like neuromorphic computing is uh, try to understand the concept more and be more motivated. Don't go into specifics too much. If you want to go into specifics, do it through an internship or project. That would be my suggestion. Because just reading about the specifics, uh, it's not going to be fun and it might actually make you hate the field. So, I mean, just if you want to get into neuromorphic computing at this stage, I don't think a lot of people expect you to know a lot about it. So, I mean, you can just aim for some project or internship directly. uh, I mean, at least I know that in BITS Hyderabad, I mean, I worked with Professor Soik Kundu, who actually left the campus, but I know a lot of other professors who are actually taking up research in neuromorphic computing. It's at a very, I wouldn't say it's very advanced, but it's a great place to start. And if you start with something like that, research on campus in these areas, you can use that to get better internships and learn more about that field. But yeah, neuromorphic computing is still an infant. So, I mean, don't expect anything structured. It will be a bit of a struggle to learn about it. That's all I'll say.
If possible, can you list out some courses which are crucial to getting into this field?
Hmm. Uh, okay, I mean, courses, I would actually say, what you learn in undergrad itself is quite crucial. So, I mean, I'll go with the BITS courses. I'm assuming that all of us are BITSians here. So, I mean, you have your digital design, which is the fundamental course for all computing. And then you have computer architecture, and then you have like analog and digital VLSI design. So the digital VLSI design part of that is quite useful. Oh, and yeah, I mean, maybe I should have mentioned this. So analog computing is also having a second wing now. So I mean, I'm just going off topic a little, but if anybody likes analog and you still want to do computing, a lot of people are exploring analog computing. And neuromorphic computing is not purely digital computing, so it's a bit of analog. So I mean, don't ignore analog. I mean, that's what I'll say. But yeah, I mean, these are the courses, and I would definitely recommend that Professor Onur Mutlu's digital logic and computer architecture course. It's an undergrad course, but it's pretty advanced for an undergrad course, and it covers all of digital logic and computer architecture. So it gives you a good idea of almost the entire stack. So that's another good course. Apart from this, so for very specific topics like neuromorphic computing or in-memory computing, like I said, it's going to be more about the papers. So, I mean, I don't have any resources at hand, but if somebody is really interested about any specific topic that I have worked on or something, just drop me a message on LinkedIn or Facebook or something. I can maybe find some resources for you. But yeah, I mean, this is what I have right now.
Thank you, Bhaiya. There's one more question. Would you mind elaborating your work that you did during your stay at the Processor Architecture Lab at Intel?
Okay. So, yeah, I mean, so basically, I mean, one thing a lot of people don't know, even I didn't know before going into Intel Labs. Intel Labs is the like pure research wing of Intel. It's not even R&D. So they do, complete research. So they work on patents and papers. And of course, that will be used in Intel products later. But they are usually like, I mean, 5 years ahead of where their products are. So that's what Intel Labs work on. And my group specifically, as the name says, they work on processor architecture research. So the the specific thing what they work on is actually in memory and near memory computing. So okay, I did a few things at Intel Labs, but I'll probably talk about the biggest one. So uh, we actually collaborated with Professor Onur Mutlu's group at ETH Zurich. So they had developed an algorithm for genomic. There's I mean this is a little advanced, but yeah. So there's a in a genomic pipeline there are multiple stages. So it's basically for DNA sequencing. So I mean even with things like COVID and all, like this became a very important area. So the last stage in genomic pipelining is called polishing, and so at Professor Onur Mutlu's group, they developed an algorithm called for polishing called Apollo, and this algorithm was great, but the problem is it took too long to run. And I mean that's the story with most algorithms these days. So yeah, I mean when I say too long, I mean genomics takes a lot of time. Like so, just this one stage of the algorithm used to take something like 2 days or something to finish because there's so much data. Uh, and so our job at Intel Labs was, to take that algorithm and design an accelerator for that algorithm. That's in very simple words what we did. So it was sort of a hardware software co-design role in the sense that first thing is we try to change it at the software level itself so that if we can get it a little more efficient or tune it a little bit more for the hardware we have. So I mean that's something we explored along with them because they were the experts in the algorithm. And after that, so I mean what we designed was actually very similar to a systolic array, but I mean in the systolic array I showed you, there is just a multiply and accumulate block, which is the processing engine. So I mean in our case we had to design a different processing engine which suits the algorithm which we have. So I mean we designed that, and you get the inputs from the algorithm, and this hardware block is sort of like in between the CPU and your memory. So if the CPU says, right, I mean, I want to do this application quickly, it triggers this hardware block, which then takes in the input, performs a lot of these parallel computations to get the output. And so, I mean, we were able to get like almost 600x speed up in that algorithm just by designing this custom hardware. So I mean that was the sort of thing I was doing. So essentially, what they do at Intel Labs is they deal with all these complex algorithms and try to come up with accelerators for that. I mean, at least my group at Intel Labs, that's their main focus.
Yeah, thank you for elaborating on the bio. It's actually really inspiring to know that you guys collaborated with a group that was under the mentorship of Onur Mutlu.
Yeah, right. I mean, it is a fanboy moment for me also. I mean, so
Yeah.
that is great. Yeah.
If anyone else has any questions, you guys can unmute or type in the chat box. I guess a lot of people here also have the question of how one should go about securing an MS in a top university in this field.
Mm-mm.
So maybe if you could elaborate on that.
Okay, I think that needs a whole separate talk. But anyway, I'll tell you what I can tell you. So yeah, I mean, there are a few components to your MS application, and one, as I mean, it might be sadly for some people, and it might be a good thing for the others. But your GPA is a very big component. If you have a good GPA, it increases your chances a lot. I mean, I always say like GPA is like money. So I mean, it's not like you can't do well without a good GPA, but it's always better to have it. So I mean, if you're starting off your undergrad or in your early stages and you want to do an MS, focus on keeping a good GPA. That would be my suggestion. And apart from that, so I mean, so essentially, I mean, the top universities, what they want to see in you is that you need to be someone who has a good idea of what you want to do and is actually put some efforts towards that. So I mean, that's where your projects and internships come into play. The easiest way is to have a big name internship and getting a letter of recommendation from that big name person. It doesn't always happen for everyone, which is all right. But I mean what I would say is just be very clear about what you want to work on, and write that statement of purpose in a very clear way. So i mean I mean in my case, so I was very clear. So I wanted to work on making computers more efficient. That was the theme of my SOP. And so I mean all the projects I did were aligned to that, or at least I showed it in a way that it was aligned to that. So I mean that's what's important. you basically need to convince the person who's reading your SOP that you have actually done stuff to substantiate your claim that you want to do something in the future. So that's the whole idea. I mean, apart from this, if your projects yield, papers, patents, and all that, that's great. That shows. I mean, so the problem is, at least at our level, the papers, I mean, the projects we work on, it may not sound very good. So if you have a paper, the person who's reading that paper can actually say, okay, there's actually something here. He's not just saying something for the sake of it. So I mean, that way having papers is very good. But yeah, I mean, I would say like GPA is number one. If you don't have a good GPA, then try to push everything else so that it makes up for the GPA. And of course, you have your GRE, TOEFL, and all that. But I mean, I don't think that's so important. Just you need to get a good score, which is above certain cutoffs. They don't they don't claim any cutoffs, but there's some implicit cutoffs. So as long as you have that score, that's good enough. But yeah, I mean, if anybody has specific questions, just contact me again. This is too short a time for me to cover everything.
Oh, thank you for answering that, Bhaiya. Um, I guess we have run out of questions. If anybody, I guess nobody else has any more questions. So I would like to thank you for taking out the time to come and give this talk. It was genuinely very inspiring to have you give this talk.
Yeah, sure.
So
Yeah, thanks everyone for attending. This was fun.
yeah, thanks a lot, Bhaiya. I guess if we don't have any questions, I guess we can conclude this meet.
Okay, great.
Thank you, Bhaiya.
Yeah, bye.
Bye. See you.